Hey, what's up, guys? This is Chung here again. So today, let's take a look at this last problem of this week's weekly contest. So number 1627, graph connectivity with threshold. I think it's a nice graph-related problem. Okay, so let's take a look. The description. So you're given like n cities labeled from 1 to n. Okay, and okay, we can skip this part. And so it says that, X and Y, city X and Y are connected if they have like a common divisor, which is greater than this threshold. Okay, so and here it just give you the definition of the common divisor, right? So for example, if we have like a number like say uh, 16 and 12. So what are the common divisor of 16 and 12? They're like uh 2 and 4, right? 2 and 4. Okay, so those are the two common divisors of this 16 and 12. Okay, because that's the definition of that, right? So okay, so that's the definition of that. So basically, the those two 16 are and 12 are only connected, right? Basically, if there's like an edge between 16 and 12, if there's like a common divisor, right, that's is greater than this threshold. Okay, and then it asks you, so okay, so it asks you to calculate the given like the n and the threshold, right, and it asks you to calculate the queries here. So it gives you a query. So the query is like the basically the two cities, 1 and 4, 2 and 5, 3 and 6. So it basically just check if those two cities are connected somehow, right? So yeah, that's basically the problem, right? So I mean, every time, right, when you guys see like this kind of like a graph problems and ask you to check the connectivities, it's most likely you need to use the union find, right? Because the union find is a perfect candidate of solving this kind of connectivity problem, right? And so what's make this one a difficult problem is that, from 1 to n, you cannot simply basically you have one to n different nodes here, right? But there's a rule, right, to connect each of the basically to draw an edge between two numbers. So the basically the rule is they have to have like a common divisor which is greater than the threshold. Okay, so basically that's the criterions here. And now the problem comes down to how can we build this graph, or how can we build th this union find data structure? Okay, I mean if we have like a union find data structure, right, with all the possible combinations, right, that set all the possible joins, right, the combinations with the that satisfy this threshold, then we can simply, after we have that a graph created or union the disjoint set created, right? We can just simply do a for each of the queries here, we can just do a find, right? We can do a find of the first element, basically the find x. If the find x is equal to the find y, right? So x and y is this is x, this is y. So I mean, after we have built that the graph, then so this one means that okay, so this x and y they are in the same, basically they are in the same group, right? So a group means they are in the same graph, which means they are somehow connected, right? I mean, so why is that? Why can't we just use try to get a common just get a common great common divisor for these two values, and then can we do that? And then for each of the common GCD of this pair here, we just compare with we compare with this threshold. Can we do that? No, right? So why this one doesn't work? Because let's say, for example, we have a 16 and 12. and uh, and this threshold. Let's say this threshold equals to 4. Okay. So if you're only looking at this 16 and 12, the biggest common divisor, right? The greatest common divisor for this one is 4. So 4 is not greater than 4. So if you're only considering this 16 and 12, then this one shouldn't be it should return false. But it turns out this one is they are somehow connected. So why is that? Uh, okay, so I think let me think of the example here. And sorry, so I think this one is not a good example. Sorry. The so I found a better example here. So this one here, 16 and 9, and the threshold is 3. So if you only by looking at this pair itself, the common divisor, what's the common divisor of these two numbers? 1, right? So there's only one common divisor for these two numbers. So 1 is smaller than 3. So if you only compare this, get the common divisor for this between these two numbers, they're not connected. But they are connected because let's say the n is 26, right? So one of the test cases is like this. So 9 and 18, right? So 9 and 18, these two are connected, right? These two are connected. What am I drawing here? These two are connected because the common divisor of these two is 9, right? And how about 16 and 18? They are uh, 16 and 18, they're like 6, 4. Okay. So and so 9 and 6 and 18 are connected. How about the 16? So for the 16, 16 and 24 are connected, right? Because the common divisor, there's like a 4 as a common divisor between 16 and 24. So these two are connected, right? And now how about so as you guys can see, 24 and 18 are they're also connected. Right? These are also connected because there is a like common divisor of 6, which is greater than 3. So that's why the 16 and 9 are also connected. So that's why you cannot simply just compare these two numbers. You have to build the entire graph beforehand, before checking those any of the queries, any of the pair inside the queries. And so the problem is how can we build the entire graph like a different connected group of set, right, beforehand. So I think while I'm drawing this, explaining these examples, I think some of you may have already seen some patterns here, right? So first, right, this threshold, that's the that's our baseline, right? So we have any of the common divisor, right, has to be greater than this 3. So which means, let's say for example, we have 3 here, so which means we need to start with 4, okay? And so let's say, for example, let's say our current threshold is 4. So what are the connected numbers with this 4 here, right? So we have 4, and then we have 4 is connected with 8, right? 8 is connected with what? With 12, right? 12 and then 16, 20, right? And 24 until n. All those numbers, they're all connected, right? Because they are all sharing the same common divisor, which is 4, which is greater than 3, right? So we can just basically we can union all those numbers together, right? And then the next one is what? It's 5, right? The 5 is what? Same thing, 10, 15, 20, 25, etc. until n, right? So all these numbers they're also connected. So I think that's now we have find the answer for this problem, right? So the solution is that the approach is that we simply starting from the threshold, right? We're starting from 5 until n, and then we just try to union everything, right? With the step of this number itself, right? And then we can just continue do a union find. In the end, we have a complete uh, joint set, right? Completely connected set for all the numbers. For all the numbers between the threshold and our n here. Okay, and so that's how we build the graph. And then later after that, we simply just use the graph to find the answer for us. Okay, cool. So I mean, once you have find the patterns here, so the coding is pretty concise, you know. Okay, so first thing first, right? The pattern of the union find. So we have a parent, right? So for the union find, we usually have a parent, right? So in this case, the parent is like is a numbers from 1 to n. I'll just use n plus 1. But since the range is only giving an iterator, we need to convert it to a list. Okay, because at the beginning, right? I mean, each number has its own as its parent, right? So that's how we initialize this. You know, for those who still don't know the union find, you can easily find a lot of the implementations for the union find, right? So first thing first is the find. So for the find, we have this. The template is like this. If the x is not same as the parents, okay, then we do this. We do a recursive findings, uh, right, with this parents. Okay. So the reason we're doing this is that, you know, while we're doing this recursion, right, we're also doing like a path compression. So, you know, a path compression is like this. I mean, I think I have explained a few times. So for those who still the first time seeing this union find or who still don't know this path compression, it's like this. Let's say we have like a list here, right? So we have a root here, and here we have node 1, node 2, node 3, and node 4. Let's say all those things, they are all unions together, right? They're all in the same set. So now when we try to find the x here, right? If we don't change anything, right? So the parent 4 is 3, 3's parent is 2, so on and so forth. And then to be able to find 4 here, right? If we try to find 4, we have to do what? We have to do basically we need to loop through 1, 2, 3, 4. We need to loop 4 times, right? That's going to be a O of n time complexity, right? But if while we're doing this the find here, let's say basically the path compression is that since this is the root, uh, the first time when we find this 4 here, we'll be removing this 4 and we'll be attach it right below this 4 here. Okay, and as you guys can see here, since we're using a recursion here, right? So while we're finding 4 here, so also we are moving 3 here. We're also moving 3 to here, 3 here, and also 2 here, 2 to here. Okay, that's the that that's the beauty of this recursion call. I mean, so only the first time the find time is O of n, but the second time when we find any 1, 2, 3, 4, I mean it's only a O1 time. That's why it's called path compression. Basically, we're compressing the path from linear to a O1. Okay, cool. So that's the find, and then the second one is a union, right? So the union is x and y, right? So we have a root. So the union, why? So when do we do the union? We do we find the root for x and y first. Okay, that's how we do the union find, right? And then we do what? We do a if R1 is not equal to R2. If the R1 is the same as R2, then we know it, they have already been union together, so we don't need to do it. Otherwise, we can just simply do a parents. So here it doesn't really matter if we do a R1 or R2. We can either assign R2 to R1, or we can do assign R1 to R2. You know, think the complete template is like we're also going to be maintaining like a rank, you know, a rank of the rank of each of the node, and every time we're only assigning the root with the lower rank to the root with a higher rank. That's basically kind of like the improvement of this union find template, but that's only to improve a speed a little bit. But we are not going to use that rank concept here because it won't affect our logic, right? Our goal is just to union everything together. It doesn't really matter. We always union to this R1 or R2, so it's okay. So now we have a union find. Like I said, now we have to build our graph, right? So the graph is, like I said, we need to start from the threshold, right? Threshold plus one. Yeah, we do a plus one, and then we stop at n, which is the n plus one, right? And then for each of now for y, right? So that's going to be our current threshold, right? So for y here, right? Y in the range of what? So the next one is the what? Like so we have 4, 8, 12, 16. So now we're at 4. We need to union 8, 12, and 16, right? So we should start from. I mean, we can either start from x or it doesn't really matter. I think we can start from 2x or x. I think yeah, x is fine because x and y it's the same, right? So of course they will have the same root. So I think it will just skip that. So I think we should start from 2x, right? And we stop at n, right? And this is the important part. So the step is the x itself. That's how we get 8, 12, and 16, right? And then we simply do a union of these two numbers, x and y, right? So that's how we do the union find. Uh, do we have to do this union find all the time? Um, Probably yes. I mean, yeah, I think this is like the naive way of implementing this. I think we can check this, right? If the y uh oh yeah, I think so. Yeah, because you know what? Because the next time, right? So next time when we are at 8, let's say the first time is 4, and then now we're at 8. Uh, I think we still need to do that, right? I mean, the 4, right? 8, and then 8 is gonna be 8, 16. Yeah. Okay. I think we can just do that. We can do a union find here. So and then later on we simply return the what? The answer, right? So we can do a quick find here. Find x equals to find y, right? For x and y in queries, right? I think that's it. Yeah. So that's how we build the graph here. And this is the final answer. Let's run the code. Hmm. Okay, so accepted, submit. Cool. So it passed. All right. I mean, pretty straightforward, right? I mean, the time complexity is since the union and find it's all they're all O1, right? So we have a ON here, and then here we also have like this is also of ON, I think. Yeah. So basically we have a O of n square time complexity. Yeah. Okay. And the space complexity is the parent, right? So the parent is O of 1. Space is O of n, right? Yeah. I think that's it for this problem, It's just to recap a bit, First, we see, okay, this is a graph problem, and it asks you to check some connectivity for this graph. So the first thing we should consider is the union find. Okay, so we have to somehow build a graph to union those numbers, those points together, right? Those numbers together. But since like as you guys have seen that for the 16 and 9, those numbers are basically they are connected by different numbers, but they're not connected because of the number because of 16 and 9. So that tells us, we have to build the entire graph beforehand. Okay, right? We cannot build the graph only using the 16 and 9. So then how can we build the graph beforehand? Now we have to think about, uh, we have to try all the valid the threshold, and with each valid threshold here, for example 4 here, we have to build 4, 8, 12, and 16. That this is the tricky the math calculation part where you can union all those numbers together because we know they're all sharing the same common divisor, and you have to be uh, I mean careful enough to find this pattern, right? So that you can use this pattern to union all the numbers for this threshold, right? So after that, it's just using that graph, the union find dataset we have been previously. Cool. I think that's it for this problem. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.